So we talked about satellites and how we derive the expression for satellite speed. We also figured out how we would make a satellite geosynchronous so that its rate of rotation around the Earth matches the rate that the Earth spins. What I want to get into now is basically the solar system here. So if we have the sun here, the sun has a lot of satellites, and those satellites are the planetary bodies. So if you're going to model the solar system, now this is not drawn to scale. You have to understand that our planets and the sun, they're all extremely so far away that they would all be dots on a piece of paper if I were to model them correctly with respect to their distances. But if you're looking at, a non-scale model here, this would be Mercury. We have then Venus, second planet from the sun. We are the third. So you got Earth here, and maybe you would have Mars over here, a little bit farther away, and even farther away you would have Jupiter. Maybe Mars out there. There's a lot more planets, but each of these we can model their orbits as circular. And we're all orbiting around the sun. So what's happening is that every single one of these planetary bodies has their own velocity. And what you're going to find is that the inner planetary bodies, the inner satellites, those are the ones that travel the fastest. Now that should make sense based on how the expression for satellite speed looked, but this is going to be going on very rapidly. As you move further out, they move a little bit slower each time, or maybe even a lot slower, and some of these things take an extremely long time to make it around, and they're actually moving at a lot slower velocities. So if you ever looked at the table of the actual period of planetary bodies, we know that the Earth's period is 1 year around the sun, but these are going to be smaller. I believe, if I'm thinking right off the top of my head, this one might be like 30 days. It's really short. And then when you go farther out, I think Pluto is something like once every 80 years maybe, or maybe even well beyond that. But there's a serious discrepancy in the periods here. What we have is each of these things is guided by the force of gravity. Force of gravity causes centripetal acceleration. Now you have different forces of gravity acting on each of these planetary bodies because if you look at them, well, their masses are different, and in addition to that, they're also different distances from the sun. So they all have their own force of gravities acting on them, and they all have their own period. And the force of gravity depends upon all those things, right? The distance and each planetary body's mass. But the one that's probably the most important is the sun. The sun we're going to call big M, and each of these are little m's. They're their own circular bodies. And actually, this is probably an awful picture because I drew Jupiter larger than the sun. I will draw Jupiter like that. Still kind of looks larger than the sun, but whatever. We'll go with it. And then what we can do is we can model these as a function of circular motion. So what astronomers have the ability to do is they have the ability to measure how far away each of these planetary bodies are from the sun, so we should know what their radii are. And then in addition to that, if we keep track of their motion, we can determine how long it takes to get around the sun. So we know how far away they are from the sun, and we know exactly how long it takes for them to get around the sun. So when you do that, you can say that, okay, well, let's look at just any random planetary body of little mass m. It's moving in a circle around the sun, and the only force acting on them is this force of gravity. Well, when we rewrite the force of gravity as g little m big M over r squared, basically we're at the exact same spot we were when we were trying to derive the expression for satellite speed. But now what we actually want to do is take a look at the expression for t and its relationship to r. So what we're going to do is we're going to say, okay, let's do this. V equals 2 pi r over t. We're going to put that into there, and when we do that, we get little m 2 pi r over t, square it, divide by r, g, little m, big M, over r squared. We can probably start to cancel out a few things here. Let's just go with mass right now. That the mass of the satellite doesn't really matter here. It's always changing. In fact, when we look at different planets in the solar system, this mass is not changing, however, though. That's the mass of the sun. So let's square that. We get 4 pi squared r squared over t. Then we're dividing by r again from there. And then this is gm over r squared. So now we've completely eliminated v from the expression, and I see period, and I see the distance r. Got some crossing out to do here. Eliminate one of those r's. What I would probably then do is cross multiply. So if I did that, I'd have 4 pi squared r, and then if I multiplied by r squared there, that would be r cubed, and then this would be gmt, and I forgot to square the t. Don't forget to do that. That came from right there, so it would be t squared there. Then last thing to do, let's try to isolate t squared, so let's divide both sides by gm. So I would get 4 pi squared over gm r cubed equals t squared, and then we'll flip it around 180, and then we'll say that t squared is equal to 4 pi squared over gm r cubed. And this is the expression that we want to look at. It's a nonlinear relationship between period and distance. What you should be able to say is, well, as r increases, t does increase, so the farther away you go, the larger your period gets. In addition to that, why this is important is because everyone always goes, well, how did you determine the masses of the sun? How did you determine the mass of the Earth? And the key to doing that is looking at the satellites. If you can look at all the satellites and get their values of t and get their values of r, we know what 4 is, we know what pi is, we know what g is. That means we can solve for m. So what we do is basically, if we wanted the mass of the sun, all we got to do is make a table of t and r for all of our planetary bodies. You would have Mercury, Venus, Earth, Mars, and Jupiter, and all the rest, and you'd fill them in, right? But then what you would do is you'd say, okay, we got to modify that data. Let's square it, and let's cube our r value there. And then when we do that, what we can do is, because the relationship is t squared equals 4 pi squared over gm times r cubed, if we make this our y data and this our x data in that plot, it's going to look like this. And your data points all of a sudden become nice and linear. And then what you do is you fit it, and you get the slope of that. And the slope of that is very important, because the slope of it is equal to this expression right there. So the slope equals 4 pi squared over gm. So once you get the slope of your line, then you're able to solve for the mass of your central body, the planet. So you can do this analysis for Earth because we have a lot of satellites going around it. You can do it for Jupiter because Jupiter has like 67 moons going around it. You can basically do it for any planetary body as long as you're keeping track of the satellites. And then once you keep track of the satellites, that's your key to discovering what the mass of that planetary body is. So we will end up doing that in a, let's say, a data analysis activity where we collect all the data on the various satellites around a planetary body and try to determine its mass, and then we'll compare it to the accepted value and see how well it works out.